All right, what up, folks? I feel like I'm behind in terms of my lecture, and I hate doing that. You have homework that's due, and I didn't even have a chance to finish lecturing on it because I only had one lecture so far. So here's what I'm going to do, and I think that you folks all like me for it. Follow me. I'm going to go into the class. So go into your own class, and you can watch this happen as it happens. But my computer screen is now frozen. One second. Sorry. It's going to take a little bit of time. It's thinking. It's a good computer, I promise. It just doesn't like me. Okay, 1 second. Come on. Work now. There we go. All right. I'm going to go into class, and I'm going to go to the calendar. You folks can join me there as well. Calendar. See the spinning bar? That means I clicked it, and I promise the calendar is going up or coming up. It's just, it takes its sweet time. All right, here we go. So I'm in the calendar, and it looks to me. Okay, wait. This is chemistry. Sorry, I need to be able to see this. I have to scroll down. Whoa, what happened? There we go. Okay, there it is. Ah, oh, not responding. Man, this computer's slow. There we go. All right, let's see. Okay, here. So this is your science class. Actually, I'm going to reject that call. Here's your math class, and here's what I'm going to do. I feel like I haven't lectured on functions 1.5 and all that kind of stuff today. So here's what I'm going to do. I'm going to take this guy, I'll drag him here. I'm going to take this one, I'll drag it here. This one, I'll drag here. We'll move this one here, and this one here. So what I did for you, and everyone say thank you, is I took your homework and I pushed it back a little bit. So what that does is it gives me a chance to say I'm going to lecture on this. So today what I want to try to do is finish off chapter 1 or functions 1 and then cover functions 2, because my goal is to always be at least ahead of what you're getting homework on. It would be unfair of me, but I see teachers do this all the time in college and in high school, to have students turn in homework that they didn't even get a chance, the teacher hasn't even had a chance to cover that material for. Fair enough? So what I'm going to do is, I said, well, since I only had one lecture, which was the one on Monday, on the 3rd, I don't think it would be fair of me to ask you to do homework on 1.5 yet if you do that. So I am asking you to finish 1.5 today as opposed to do it last Monday or this past Monday. But that's because I'm going to finish lecturing on that today. And it shouldn't be something too bad because that's just functions of a straight line, I think, is 1.7 or 1.5. Got it? So the quizzer that was due today, I pushed it back to Friday. You still only get one shot, but at least you have 2 more days to kind of stress out over it. I pushed your chapter 2 homework back to next week, and I pushed your stuff that was due on Monday and Tuesday to be due on Wednesday and Friday, or Thursday. Sound good? All right.
Thanks.
Yes, you may use that. Can you close the door? Is that door open?
Nope, it's just how loud they are.
Who is that? All right. Give me a second. Let me go. That was the teacher that was that loud. Ah! All right. Anyway, let's do this. All right. So today I want to cover straight lines with you, and I think that this is basically still a review for you, and then I'm going to finish off chapter 1.2. Here's how things are going to work. Technically, I have you folks starting at 12:45. I don't mind doing that. I think that that's a good idea. I won't go for 2 hours today in class. What I'm going to do is I'm only going to go for 2 hours every other week, every other Wednesday. Sound good? What I'm going to do is I'm going to kind of go for about an hour and then finish off. And then after that hour, what I'll do is I'll open that up to just straight tutoring. If you folks want me to stick around for 2 hours, I will. If you folks want to leave, you can leave. That's fine. Sound good? Now, I'm going to do the same thing for chemistry. I'm not going to go chemistry from 125 to like 340 because I think that's what we have set up, right? I don't know. You're not in chemistry, but some of you are in my chemistry class. Some of you folks are staying for my chemistry class. I'm not going to do it for 2 hours today. I'm going to lecture for maybe an hour and a half, or maybe an hour, and then I'll end class early. If you want to finish, if early, if you want to leave, then that's fine. If you want to stick around and get help with homework problems, I'm open to that as well. I just made the class 2 hours so that I can say I have 2 hours to use. You know, you have nothing really to do for these next 2 hours. But it doesn't mean that I'm going to hold class that long. I really have those 2 hours because I want to make it worth your time when I bring you in for lab and that kind of stuff. And for Algebra 2, we don't necessarily have a lot of labs, like we're going to do lab experiments. Those are more for science and whatnot. But I will try to think of some labs that we can do. Also, what I would really encourage that for is a lot of students like to come in and see me face-to-face and work with me there. And some students find that really helpful. So what I'm doing when I have you guys coming in for math lab is really teaching you in a face-to-face environment, which, or at least giving you the opportunity. Obviously, if you're on the Big Island, you can't do that, so, what you going to do. All right. One other thing I want to show you, one other change I want to show you is, now you can see how many courses I have. So you guys are like, I have so many courses. Yeah, look how many I have. They're not even displaying all of them. I think there's other 13 more.
You teach all of that?
I'm involved with all of them. I teach most of them. All right, the last change was this. They screwed up our the times when they gave it to me. Now I keep changing them, and I apologize. Not my fault. They gave me a sheet, and it said, I think I said that classes start on Mondays at 12:45 and end at like 1:30 or something like that. Well, actually, Monday classes are going to start at 1:30 and end at 2:10. Got it? Today's class is going to go from 12:45 and end at 2:10. Technically, on the paper, I said it ends at 2:10, and I just finished telling you I'm going to go for maybe an hour. And then you guys are free to go. And free to eat a sandwich between now and chemistry if you folks are taking chemistry for me, or get lunch or something. Yeah, so Monday is at 1:30. And again, that's not my fault. I put up the right time. I don't know. They came back to me and said, hey, ours is different. And I said, well, the original one you gave me said this. So anyway, I'm not trying to blame anybody, but it's not my fault. All right. Let's cover lines then. Let's get into this thing. All right. Are all the classes recorded? Yes, all the classes are recorded. And I just showed somebody, one of my assistants here, that how to access the recordings. First of all, you can go to conferences. And when you go to conferences, you can see the recordings that they do. For some reason, Monday's conference wasn't recorded. It says no recordings. And this kind of actually highlights my point. I hate the recording button that big blue button does. This is a big blue button, and if I press this button up here, apparently it records it. But that recording doesn't always work. The audio is junk sometimes, the video is glitchy, and not only that, but they only keep the recording for 2 weeks. And then after 2 weeks, they just throw it away. So what if you folks want to review something that was more than 2 weeks ago? Well, tough. Got it? So here's what I do, is not only do I record on the Canvas, but I also record the computer screen and post it up in a YouTube video. Please keep in mind that it takes me it takes me about a day to process the video, so the video doesn't come up like exactly right after class is done. Especially since I got to go and teach chemistry right after this. Like literally I have a 5-minute break, then go and teach, so I can't upload these things. So I'll show you where to find those things. I'll put them inside of our class over here. And if you look right over here, it shows you, I put up Monday's archive right here. It says, watch August 3rd, 2015, Monday's archives. It's on functions. Got it? And that's where we talked about chicken katsu. You missed the lecture on chicken katsu.
No, don't worry.
It was a tasty lecture. Yeah. Anyway.
I don't want to miss the food.
All right. Anyway. Sound good? So those are actually posted to YouTube. What I like about that is, to me, the recordings are clearer. The quality is better, and and they never get deleted. So anyway, I'm just letting you know. Sophia, what did you miss? Mr. Dalde was super awesome, and he moved some of our assignments back, and he put 2 days quiz due on Friday. Mr. Dalde was basically just explaining things about like where the archives are and everything, so you didn't really miss anything. And we wasted 10 minutes doing that. So now we're going to start talking about class, and hopefully I'll go for only an hour, because Mr. Dalde likes to talk a lot. And rarely ever does he talk about himself in third person. It's up right now for some reason. All right, here we go. So the only thing I want to cover with you in section 1.5 today is, and Monday, oh yeah, the Monday virtual class has changed. They told me that I needed to change it, but they told me the wrong thing in the first place, so not my fault. All right. Let me just pull up a few things, and I'll talk about these things while I'm going through it. Yeah, all right. Sophia, you brought up a very good point, and I'll talk to you about that after I'm done lecturing today. That's right, I remember. She was saying, hey, why is the square root function a function, and yet it's defined with, you know, it looks just like that weird function I gave you. In fact, you know what? I'll tell you what, Sophia, why don't we talk about your problem right now? It's a good point. Just give me a second. My computer is loading up Paint. All right, here we go. I'm going to zoom out. I'm going to zoom in. Come on, computer. Think. Think faster. Think faster, faster. All right, anyway, hey, while my computer's thinking, why don't I ask you some questions? What is the square root of 4? 2. Ah, Sophia says, well, Bradley's only half right. She's saying it's 2 and -2. What is the square root of 4? Is it 2 or is it -2? Or both, according to Sophia.
No, wait.
All right, here. It's kind of a tricky question. All right, check this out. If I ask you, what is the square root of 4? Whoa. Let me zoom out just a little bit. Okay. And I want to stop this infernal racket. I should have just put it on mute, but anyways, it's not going to let me do that now. So we'll see what we do. All right. If I ask you, what is the square root of 4? The answer is actually 2. Okay? But I think I see where Sophia is coming from. If I say, if x squared is equal to 4, got it? Then the question becomes not what is the square root of 4, but what can x be? And your answer would be x can equal to 2. That would be fine, right? Because if x equals to 2, then I plug a 2 into here, and that would be 2 squared, which is 4, right? But in this case, x can also be, I don't know why I can't see the chat. What's going on with that? All right, there we go. What's going on? Why is this thing blowing up? Here's what I'm going to do. I'm going to turn off the volume over here. Whatever, it doesn't work. Okay. If x is equal to 2, this works. But if x is equal to negative 2, this also works. Got it? So here's what I'm saying, all right? And this is a little weird. Now, what Sophia is thinking is, hey, the square root function is not a function. And I would say, I see where you're getting at, Sophia, because if you were to take the square root of both sides, like this, what you have to do is you have to remember to add in a plus or minus. So you have x is equal to plus or minus the square root of 4. The square root of 4 is also known as 2. And that's where Sophia is getting this idea that x is equal to plus or minus 2. Okay? Keep in mind that this is kind of a side discussion that we're having, that I'm trying to answer one of Sophia's questions. If you're confused, just kind of hang for now. But also keep in mind that this is an interesting discussion. Anyway, if I had something like this, y is equal to plus or minus the square root of x, I'll show you what that graph looks like. And this is where Sophia is getting, this is why Sophia is talking about the square root function, because she looked at this graph and she said, I recognize this graph. And when I draw it for you, after you folks have done the homework, you folks will recognize this graph as well. I'll show you what it looks like. If I were to just include the positive version, it would look like this. That is the square root. That is a graph of the square root of x. But I need to include both the positive and the negative version, so the graph looks like this. Do you recognize this from your homework? Did you do the homework?
No.
Okay, well, that's why you don't recognize it from your homework. Some people are recognizing this. This was like question D in one of your homeworks, right? And the answer is, the answer to Sophia is, or the question asked is this a function? And the answer is no, it's not a function. Why is it not a function? And some of you folks said very simply, it doesn't pass the vertical line test. That's easy. You got a vertical line, it crosses at 2 points. And then Sophia is saying, wait a second, this is a pretty popular function, the square root of something. You know what I mean? I should be able to graph that. Why is that not a function? Is that what you're saying to me, Sophia? Why is the square root of x not a function? Well, I'll tell you why. Because whenever we graph the square root of x, we only graph the positive version. It always looks like this. The reason being is exactly because if you include the negative version as well, it tears that thing down and makes it no longer a function. So we kind of, it's almost like we kind of it's almost kind of like we blind ourselves to half of it, because that second half makes it not work. And why would we do that in math? Why would we kind of say, well, it doesn't work unless I cover one eye, so I'm going to cover one eye from now on? Well, it's because the positive, this picture right here has a lot of properties for us that are very important to us. So we understand, so what we do is we kind of say, Well, also remember that you should include the negative side. It's kind of like the mirror image on the bottom side. Does that make sense? I'll be honest with you. This is kind of a heavy discussion to have at the beginning of class. I was going to start off with lines, y equals mx plus b stuff. But Sophia brought up a good point, and so I kind of wanted to talk about that one. Are we cool? Yeah. It's not that you excluded this. It's not that this wasn't important. This was actually a part of your homework problem. It's just not all of you, or maybe only one of you, recognized that this was actually a square root function. The graph that looks like a sideways parabola. And the sideways parabola, those are not functions. Cool? If you're confused, by the way, my assistant here, do you want to sit there to see your face?
Yeah.
All right.
Hello.
This is one of your classmates, and she's sitting next to me while we're in class, and that's because that's the kind of help that she wanted to have. So feel free to come in if you need to. If you're confused, what I would recommend doing is before you get completely confused, watch the video on Monday,
Okay.
and then and then you'll learn about how we talked about what a function is and the vertical line test and those kinds of things. Are we cool?
Mm-hmm.
So before you start asking me a bunch of questions about, like, I'm so confused, watch the video at least. Got it? And that goes for everybody. If you folks want to come in and ask for help, what I would ask you to do is at least watch the videos first. All right, half of it, but only. All right, here we go. So we're going to talk about functions 1. We're going to talk about slope equals rise over run. This is stuff you're familiar with. My computer is the slowest one in the world. I hate to say it, but I think that I've almost finished my time. Well, no. I told you I would go to about 11:40, yeah? So. It's time for a new computer. All right, you say that, and yes, we all got new computers. We got MacBook Airs, and they're super nice. That's why the video camera looks so good. It just brings my beautiful face in HD to you. The hard part is the MacBook Air doesn't play nicely with this Canvas program. So I need to use the old computer for some parts of this lecture. You know, to be able to draw on the screen for you. Got it? So anyway, that's the problem that's going on. All right. Definition, the slope. What is the slope of a function? You guys remember this from back in like 5th grade days? Rise over run. Got it? It's how far up you go divided by how far across you go. Now Lucas threw up an equation, and I'll write that equation down. Lucas threw up the equation y2 minus y1 over x2 minus x1. Do you guys remember that equation?
A little bit.
Or you've once seen it before, and I'm surprised that Lucas remembers it.
Yeah, me too.
Right? Okay. All right. And I like how you guys are being honest. I kind of got it. All right. Here's basically what's going on. I'll show you folks the gist of it. All right. That's called a coordinate plane. This is the x-axis. This is the y-axis. Now we are starting at least where you folks are comfortable, right? You've done this before.
Mm-hmm.
Got it? Now, there are 2 points. Let's make up 2 points on this axis. Let's call this point right here. I need 2 points to describe that 1 point right there. I need 2 numbers to describe that 1 point right there. I need an x value and I need a y value. Why don't we call the x value x1 and we'll call the y value y1? Because this point is actually known as point 1. Sound good?
Yeah.
I'm going to make some other point over here, point 2. And I'm going to call its x value x what?
2.
x2, good. And I'll call its y value
Y2.
y2. That makes sense because, I mean, it's the second point. Got it? If I have a third point, I will have x3 and y3. Got it? All right. So when Lucas is saying rise over run, what he's saying is in order to travel from this point to this point, you could go in a straight line like that. Got it? Or if you think of this as you're an ant on a paper and you want to go from this place to your girlfriend's place. Okay, you could go straight. Or you could go up first and then across. Right? Now, how far up would you have needed to go? And how far across would you have needed to go?
Should I answer that? Or
Yeah, answer. Go for it. If you know the answer, answer.
I don't know. There's no units.
Okay, fine. I'll tell you what. If you're uncomfortable because there is no numbers, I'll make numbers for you. Let's make this. You start over at y equals 3, and you end over at y equals 5. How far up did you have to go?
2 units?
2 units. How did you figure that out?
5 minus 3 is 2.
5 minus 3 is 2. I love it. Good. Now, let's back up and do something a little bit more abstract then. You don't start at 3 and 5. You start at y1 and you end at y2. How far up did you go?
I genuinely don't know.
Well, it's whatever y2 is minus y1.
Oh.
Right? Whatever the top is minus the bottom. So I could just say y2 minus y1.
And that would be the answer.
Right?
That would be an answer.
Right.
Okay.
And then what you'll say is, well, it's y2 minus y1, but you didn't tell me what y2 is and y1 is. So until you tell me that, I won't be able to give you a number. But as far as like figuring it out, you just take the y2 and subtract the y1.
Mm-hmm.
Fair enough? All right. Let's do the other one. How far across would you need to go? If you end at x2 and you start at x1.
That would be x2 minus x1.
x2 minus x1, and then you say something smart and condescending like, well, Mr. Daldy, you still haven't given me numbers, but if you wanted to figure it out, you would have to first tell me what x2 and x1 is, and then I would just take x2 minus x1.
Oh, and that's where this whole equation comes from.
And if I want to talk about how far up you go divided by how far across you go, it's really that, which is really the equation that Lucas pulled out of his head.
Okay, that makes sense, yeah.
Fair enough?
Very clear.
Good. So I don't ever actually want you to even memorize equations, to be honest with you. I want you to understand the concept of rise over run. All right. Now, why is it not run over rise? Why don't we always talk about, hey, how far across you go divided by how far up you go? And I'll tell you the reason why. Because I said so.
Okay.
Now, I hate saying that, but really, that's it. Because we could have said math is going to be done where we measure the run divided by the rise, and that is the new slope. And technically, I could go through math and teach you that, and you guys would actually be fine if only Mr. Dalday was your teacher for the rest of your life.
Yeah, okay.
As soon as you had a different teacher who uses the rest of the world's convention, you know what I mean? Then you would get screwed up.
Yeah, it's like America versus all the other countries.
Yeah, exactly.
Yeah.
It's like America versus all the countries. But if Mr. Dalday was your teacher for the rest of your life, and then you just had, and I told you slope is run over rise, then you actually would be fine. We'd be able to build buildings and engineers as long as we didn't use any engineers who learned from anybody else besides Mr. Dalday.
Yeah.
Right? So it's kind of one of those things, it's a convention. It's because that's the way things are. Why do we read from left to right? Because somebody said so. That's not true around the rest of the world, but because, it's just because that's the way Americans do it. Now, slope being rise over run, that's kind of a universal, everyone uses that around the rest of the world. I've never seen anyone use run over rise. I'm just saying, you know what I mean? All right. Let's see. In the table below, I want to figure out the slope of these things. Okay. In the table below, I want to figure out the slope. And so here's what I would do. I would take any two numbers, or any two pairs. So this 1 is tied in with that 56. This 2, the input for this thing is 2, the output is 52. The input is 3, the output is 48. Got it? It's only different answer because I think it's rise over run is the norm, and if it's run over rise, you wouldn't question. Oh, no. Bradley, the reason why run over rise would still work. It just, I would be teaching you folks. I guess it's kind of like if I wanted to play a dirty trick on my 3-year-old. I'm teaching him colors right now. If I wanted to play a dirty trick on him, I would forever tell him, this is orange, right? And as long as he lives in my house, he'd be fine. Because everything that looked blue, he would say is orange. But I mean, that's fine. He could live with that. You know what I mean? Until he stepped outside of the house and actually said, hey, look at that orange sky.
Yeah.
Then he would get screwed up. So it's kind of a way of convention. It's a convention that we've all agreed upon. This is not orange, this is blue. You see what I mean?
Yeah.
Okay.
I got about that before.
All right. So, let's do this one. If I want to figure out the slope of any of these points, let's choose 2 points. And I'm going to write it like this. 156, I'm going to put a little parentheses around them. That means those are an ordered pair. Those are stuck together. Let's choose another ordered pair. Choose any one.
5 over 40.
5 over 40, got it. Not 5 over 40,
Or
but
5
it's
40.
5 comma 40. The input is 5, the output is 40. It's not 5 divided by 40, it's 5 comma 40. Yeah, run over rise would still work, it's just unconventional. All right, we're getting into a long discussion on this run over rise thing, so I'm gonna drop it after this. But what I'm saying here is this: if you were an engineer and you designed a building and you said run over rise, you know, and you stated at the beginning of your paper, you said I'm going to use run over rise as my slope, right? Your building would end up being sideways. But if everyone else who helped you build the building, like the contractor and the construction worker, all took math from Mr. Dalday, who screwed up and told everybody run over rise, they would actually build the building correctly. It's kind of like everyone being wrong makes it right.
Yeah.
So anyway, all I'm saying is it's rise over run just because somebody at the beginning of time decided I'm going to make slope rise over run. Done. All right.
Yeah.
So I chose 2 points. Got it? All I do is I plug it into my formula. I say delta y over delta x, and I'm using different notation because you're going to see different things. This delta y just means the change in y. It means how far did it change from going from one to another. Now, I started here, I ended here. So how much did the y value change from going from one to the other? It's arithmetic. Lucas says 16. I think Bradley says 16. Is that what you said? Sophia says, Lucas says 16 and then he said down. What do you mean by that? Because I was just about to say 16 is wrong. 16 down from the previous. That's also known as negative 16, by the way. Right? Because you ended 16 points below where you started. So it's negative 16. How far up did you go? I went down 16. I went negative up 16.
Okay.
Does that make sense?
Yeah.
And how far across did you go? You ended at 5, you started at 1, so you went across 4. Okay. So your answer is, your slope is negative 4, because 16 over 4 is 4. Done. Now, I like what Sophia is saying. Sophia, I think, is making this thing about like, well, wait a second. What if I didn't choose that? What if I started here, 5 comma 40, and I ended here, 1 comma 56? What if I switch those? Wouldn't that give me a different slope? Doesn't it then depend on which one I call my beginning and when my end? Well, let's try it, okay? Delta y. What is your change in y? Using this one. I started at 40, I went to 56. What did I do?
I don't know. I don't get it. I honestly don't get it.
Okay, all right. Here's what I'm saying. Okay. In the first problem, I started here and I ended here. Okay. In the second problem, I switched them and I said, well, what if I start here and I ended here? I basically just started at the second point. And
Well, am I subtracting something from something?
Well, yeah.
Would I be using this?
Your delta y is the y2 minus y1. The y2 in this case is 56 minus y1.
Oh, okay.
So it's 56 minus 40 is also known as 16. The delta x is
MBTA.
1 minus 5, which is what?
1 minus 5 is negative 4.
Negative 4. What is positive 16 minus, or divided by negative 4?
I don't know. Positive.
Negative 4.
Yeah, sure.
That's it. Hey, it's the same slope.
Okay.
So what I'm saying here is that the math fixes itself.
Yeah.
You only really need this equation. You don't need to worry about like, oh, as long as you make sure you specify which one you started in and which one you ended in, that's not going to necessarily, like, if you chose if you chose the wrong starting point, as long as you stuck with that convention, the math will work it out. The math will fix itself.
Okay.
That's what I'm saying here. Does that make sense?
Sort of.
Okay. All right. Another way to say this, let's see. It is important to know that any linear function, if you choose two inputs that are exactly one apart from each other, in other words, if delta x is equal to, oh, yeah, that's a dumb important thing to know. I'm not even gonna fill in the blanks for that. Don't memorize that. Another way to say that this is. Okay, no, that's all right. I guess I don't want you to learn that rule because that rule applied to only a very specific thing. What I want you to understand is this idea of rise over run. We cool?
Yeah.
All right. This chapter, or the homework due today, is asking you to cover stuff that is. The homework due today is asking you to do stuff that is, calculating slope, so you guys should be able to do that. Can we start up on chapter 2 now?
Yeah.
All right, chapter 2. All right, let's do this one. So what we're learning how to do now is creating graphs. And a graph, all right. So there's a bunch of different ways to describe a function. One way is to use a formula, like f of x is equal to 2k plus 5, or something like that. Or maybe, yeah, let's make it f of h equals 5h plus 10. Okay? Now, we talked about this a little bit. But f of h equals 5h plus 10. The reason why I have this f of h is the way we read this is f as it depends on h. This isn't f times h. Okay? Just wanted to make sure you understand this. It means that the equation that I'm going to have here is going to have an h in it. That's what it says.
Okay.
Okay? And so I could use a formula to describe it. I could use words. Here's words that would describe this function. Say you want to come and work for me, I'll give you $5 an hour, and just for showing up, I'll give you $10. So this would be how much money you would make depending on how many hours you work. If you work 3 hours for me, you would make $25 because you would plug in 3 for H.
And then times the 5.
Then multiply by 5, you get 15, add 10. There we go. So I described the function using using an equation. I described a function using words. My words are, you want to come and work for me, I'll give you $5 an hour to pull weeds, and I'll give you $10 for showing up that day. Yeah. Yeah, exactly. There we go. Bradley is saying, oh, maybe you work at a restaurant and the restaurant is gives you $5 an hour. The rate is $5 an hour, and you always make $10 in tips.
Okay.
You know what I mean? That's like 10 extra without even working. Not without working, but
so you're still getting paid.
Yeah, yeah. I guess maybe yeah. It's a little weird to talk about pay as this in this way because, to be honest with you, I don't ever give people $10 just for showing up.
Yeah.
You know, you're going to show up, you're going to have to do some work before I give you money. But anyway, let's pretend that that's the function. I could describe this function as a table. I could make a little table, and I would say H, and I would say f of H, right? And then I would say, all right, if H is 0, how much money did I make? $10. If H is 1, I made $15. If H is 2, I made $20. If H is 3, I made $25. Got it?
Yeah, I guess.
So that's a different way to represent a function. Another way to represent a function is using a graph, and you could make it like this. You could say, here's a graph of H, and here's a graph of f of H. F of H, I don't know, maybe you maybe you would want to call it P of H instead. The reason why I'm thinking is because that would be like profit of H. You know what I mean? Profit as it depends on how many hours, how much money you made, or, you know, I don't know.
Yeah.
So we can call these functions different names, you know, to maybe help describe them better. But here's what that graph would look like is you would be able to kind of create the graph from the table. You would say at 0, I had $10. At 1, I had 15. At 2, I had 20. So your graph would go up like this. Cool? Mm-hmm. Now different form representations are used for different things. Sometimes the graphs are really nice to look at. They're very pretty, and I like looking at them because I like seeing trends. I like seeing kind of if you were to ask me, well, what happens if I work 12 and a half hours? Or like 2.5 hours? How much money would I make? You know what I mean? Mm-hmm. What I would like to do is I would tell you, okay, if you want to get a ballpark figure, I think the quickest, easiest way to answer that question would be to look at the graph. Because you just basically look right between here, and you see how much money that gives you.
Oh, yeah. Okay.
Okay? If you want the exact number as to how much 2.5 hours would do, I would want the equation.
Yeah.
You know what I mean? And then if you weren't asking for, like, things that are not on my table, but if you were asking for, like exact hours, like if I worked 4 hours or 5 hours, I probably would want the table. So look at the table.
I want to see if I can do it right.
In almost none of these scenarios would I want you to actually tell me the form, like describe the function in words, though. I'm just letting you know. You know what I mean? I don't feel like that is the most efficient. It might be the easiest way to understand, but it's not the most efficient way of helping people out.
Would that be the right?
That looks good.
Okay.
Yeah. All right. So what we're doing here is we're exploring how to we're exploring functions as it's represented by graphs. That's the important part that we're doing today. All right. So Kai is filling a cooler of water at a constant rate with a hose. Kai walks away for a moment. During the absence, the cooler plug comes out, and the cooler starts to drain at a rate that is a little faster than the rate that it's entering the cooler. A few minutes later, Kai discovered the cooler is leaking, and reacts and plugs he reacts the plug or reattaches the plug and continues to fill the cooler until it's full. Graph the height versus time. Okay. So let's think about this. Here's time. Here's height. Okay. I've got a cooler I'm filling it with water. Got it? So tell me about how the height goes up as time goes on. All right.
Because since you're filling it,
It goes
the more
up.
water you put in, the higher the height of water will be.
Right. As time goes on, the height gets bigger. At time equals 0, the height is what?
0.
Is probably 0. He started with an empty cooler. And the reason why I say it's a straight line is because they literally told us the words at a constant rate. He filled up the thing at a constant rate, which means it's not a curvy line. It just went up constantly. Got it? Now, my second question is, at some point, the plug falls out. Actually, I shouldn't draw a solid line. I'm going to draw a dotted line. At some point, the plug falls out. So, is this my graph right here?
Wouldn't it be going down if the plug was out?
All right. Well, I have a question. You guys are disagreeing with me and saying that's not what it looks like if the plug falls out. What would this, if this were the graph, what would have to be the same? Or what would the scenario be then?
Then the water level would be the same once he stopped filling it in? Or, I don't know.
Now, this is when the plug fell out and Kai is not looking at this point. Yes, I agree with you, Sophia. It said it was emptying faster than it was filling up. So my graph that I just drew is wrong. So what I'm asking you is, even though I drew the wrong graph, what would the scenario have to be to match that what I drew? I'll change it, and I'll admit that I did it wrong, but I'm wondering.
Wouldn't you just have, I don't know, wouldn't it just be staying the same, the water?
Well, water's still coming in, right? The hose is still filling up this thing.
Oh.
But the water level is not changing. It's staying the same.
Does that mean
There we go. There we go. Exactly what Bradley's saying. He's saying if that were the scenario, then it's filling up just as fast as it's emptying.
Oh.
Right?
Wow.
Right.
Okay.
Got it. That's easy. All right, good. But I agree with everybody. That's not what the graph looks like. The graph probably looks something like this. Okay? And then, at some point, Kai's like, oh, man. And he plugs it back up. And then the graph looks like this. Everyone agree?
Yep.
Okay. I got a bunch of yeses. I'll be honest with you, I'm a little uncomfortable with the graph I just drew. The last part. It's a small thing.
Well, is the slope of that part different than the slope of the original line?
Yeah, there we go. This slope looks like you turn on the hose on full blast or something like that, right? Yeah. No. The slope should probably be, that should be wrong. The slope should probably be about the same as what it was before. Because you were using the same hose. You just plugged it up. So that's the only thing that I would say, I would give pause to say that I like this graph better.
Yeah.
Do you guys agree?
Yeah.
All right, good. All right, let's try the next one. A flight from Honolulu bound for Hilo leaves the gate on time, but the plane has to wait at the tarmac to be cleared for takeoff. Finally, a few minutes later, the plane is cleared for takeoff. The flight is approximately 1 hour. When the plane approaches Hilo, the pilot is instructed to circle the airport twice before cleared for landing. A few minutes later, the plane lands to park at the gate. Graph the distance of the plane to the air traffic control tower in Honolulu versus time. Whoa. Okay. So, I'll tell you what, there's a lot of parts to this thing. Why don't we just kind of take it step by step? Cool? All right. So, let's just assign times here. Okay? Let's say at 12 o'clock, flight leaves. I'm just trying to get an idea to help me get my story nice, okay? And then it says, but the plane had to wait on the tarmac to clear off. Finally, a few minutes later, the plane is cleared for takeoff. So let's say not 12 o'clock flight leaves. Let's say 11:42 or maybe 11:57, flight leaves. Not flight leaves, but board flight. Okay? A few minutes later, which is 12 o'clock, flight leaves. Good. The flight goes on an hour-long trip to Hilo. Got it. So at 1 o'clock, flight gets to Hilo. Cool? And then the pilot is asked to circle around the thing for twice before landing. All right. So maybe 1:20, the flight lands. Lands. After circling. Good? All right. Let's graph that story. Here's my time. This is 11:57. Here's 12 o'clock. Here's 1 o'clock. Here's 1:20. I'll make this 1:10. This will be 1:20. Sound good? All right. So, between 11:57 and 12 o'clock, how far is the plane away from the tower?
Between 11:57 and 12 o'clock?
Yeah.
3 minutes?
Yeah, for those 3 minutes, is it far away from the tower? Is it moving away from the tower?
What tower? I don't even...
It's close. It's close. Exactly. Let's make it a small number. And I'm going to make it a horizontal line because it's not moving. It said for a few minutes between 11:57 and 12 o'clock, the plane was stuck. It could not move. Got it? Now, at 12 o'clock, what happens to the plane?
Takes off.
It takes off. So maybe we can even make it a little curvy and say it builds up speed, and then it flies at a constant speed all the way to Hilo. Got it? Oh, by the way, this is distance. Maybe I'll call it d of t, because it's the distance as it depends on time. Got it? All right. Does it say constant? No, it didn't say constant. But planes usually build up speed and then they get to a constant speed. You know what I mean? Like when you're driving from Waianae to town, you kind of build up to a constant speed of 55 miles an hour, and then you go at that constant speed for 55.
Yeah.
Until you get there. So I'm going to assume that it's constant. I could make it curvy, maybe. All right. Now, at 1 o'clock, he has to circle around twice. So what does that mean? That probably means he turns around and goes in a big circle. Let's make it like a 1 mile circle or something like that. So does he get closer to the Honolulu Tower? I mean, it might even be a little bit closer, but does he get closer technically when he makes a circle?
No, I don't know.
Think about this. Think about standing and watching somebody make turn around in a circle. Did they get closer to you?
Aren't they just staying far away? But
even if they're far away, did they get a little bit closer to you?
I don't know.
All right, fine. Here. Stand over there.
Yeah.
All right. You ready?
Yeah.
I want you to face, stand further. Good. All right. I want you to face away from us. All right. Actually, I want you to take a 90-degree turn to the left.
I don't know. What do you mean, 90?
Turn left. Good. All right. Move the table. Push the table. All right. Okay. So Ikeja is standing right in front of us, and we're talking about the distance between you and the camera.
Yeah.
So I want you to walk in a circle, slowly.
My own's,
Yeah.
Does it not matter?
No, it should be a big circle.
Okay.
Not a huge circle. That's perfect.
Oh, yeah, so I'm getting closer, but then I'm getting further.
Yeah, you get closer and further, and then you get closer and a little bit further and further and further, and then you get further again. Perfect, and you get closer and further. Good, exactly. You guys couldn't see? Oh, that's a bummer. It was awesome. No, I had it on the video camera, and I just had her walk around in a circle. But basically, she gets closer and further, and then closer, and then further. Does that make sense?
Yeah.
And at the end, at 1:30, the flight lands. So, you know.
And it gets closer and closer until it lands.
Well, no, it just stays there. It
Wait.
stays the same distance away from the.
What is the airplane even getting closer to? I don't understand what the.
The original place that we're talking about it getting close to is the tower at the back in Honolulu.
Oh.
So that's why your airplane kind of stays at a constant thing.
Okay.
Over there. Let's say the airplane just died and it never moves again. It is that distance away from Honolulu Tower for the rest of eternity.
Okay.
Does that make sense? So the circling actually looks like this. In fact, if some of you have had like a little bit of a taste of trigonometry, this is a sine wave. Of course, if you don't know it, don't freak out, don't worry about it, but it's not going to be a circle. You're not going to have this. Which I think that some of you folks would want to do if you were talking about a circle. Right?
I would have straight up just put a circle on the graph.
Right, you would have
honestly.
straight up done that.
Yeah.
Right. I got a question. What's the problem with the second one I drew?
I don't even know. I don't know.
There's a glaring problem. There we go, Sophia. That's not a function.
What would it be then? If it's not a function, what does that make it?
No. Look. All right. Even if I didn't draw the circles going up, if I drew the circles going down, if I said, okay, he circled then, like this, it's not a function. Because exactly, Lucas is saying, like, over here you're going forward in time, and then remember this x-axis is time. So when you go backwards over here, what are you doing? You're going backwards in time? Are you kidding me?
Okay.
Time didn't go. Yeah, I know.
I
I
wasn't
know.
paying attention to that. Okay.
What the G? I don't even know what that means. But
Oh, time travel would complicate math a lot.
yeah. So we are excluding time traveling from the physical reality here.
Yeah.
Exactly. And the reason why I say it's not a function, you can immediately take a look at it and just say, hey, there's a vertical line. It crosses at more than one point. Doesn't pass the vertical line test, not a function.
Okay.
I would in a section that is teaching you how to graph functions, I would be worried if the things I give you were not actually functions.
Yeah, that's problematic.
Yeah, everything I give you is going to be a function if you're going to graph it, or else then Mr. Daldy would be a real jerk. All right, which he could be. I don't know, maybe. Technically, my class is finished. Would you guys mind if I keep going?
Well, what time is it?
It's 1:45.
Oh, yeah. Still haven't read.
All right, I'm just going to keep going. You can leave if you want. You can stay. I think my chemistry class starts at 1:30. Is that right? No, my chemistry class starts at 2:15. So I'm not going to go to 2:15. There's no way. But I'd like to finish off section 2.2 as well. Oh, did I skip 2.2? I went over 2.4. Excuse me. All right, I'll go back to 2.2. I want to finish off chapter 2. That way I can say, hey, next week do chapter 2 homework. All right, anyway. Creating the graph. They're passenger on a flight to Honolulu bound for Hilo, just like in the scenario above. But you're afraid of heights. You're apprehensive as the plane takes off, is seated at the window seat and is paying close attention to the altitude of the plane. Your nervousness persists for the duration of the flight and subsides as when you reach the gate at Hilo. Graph the altitude of the plane versus time. Okay. That whole story had nothing to do with your nervousness. They just threw that in there because they were trying to confuse you. But anyway.
That's always fun.
All right. Let's make the complementary graph to this thing. Here's 12 o'clock. Here's 1 o'clock. Here's 1:10. Here's 1:20. All right. Between 11:57 and 1 o'clock, where are you? How high off the ground are you?
You're not, right? Because
You're not. You're not off the ground. You're on the tarmac.
Yeah.
Between 12 o'clock and 1 o'clock, What did you do?
You took off and started flying.
I would say the graph looks kind of like this. Right?
Yeah.
Maybe more like this. Okay, what is that flap at the top? I'm not sure what you're talking about here. I would say it looks more like this. To me, this it says, all right, you're taking off, you're going up, right? You go up to the altitude that you need to, and then you, no, this isn't talking about speed, this is talking about height now. You go up to the altitude that you need to, and then you just kind of level off and go there for the rest of your flight. As you approach helo, you kind of lose altitude to kind of prepare for landing. Right. The y value is a different y value. Above, the y value was the distance away. Below, this is the height. We're talking about the altitude of the plane. All right. Now, at this point, the helo tower says, "Hey, brother, we got some planes on the tarmac. We never knew you was coming in this quick, so you know, you need to you need to circle around a couple times so we can clear them out." So what happens? You guys go like this, just like before.
No, right? Because they need.
You guys said no. Well, what would the graph look like then? Huh? So smart then. What? Yeah, exactly. You would stay at the same altitude. Very good. Because even if you're circling around, it didn't mean you were going up and down and circling around at the same time.
I want to kill the people on the plane.
Yeah, exactly. It'd probably just kind of look like this. You'd stay at the same height. And then over here, by the way, what would this scenario look like?
Wouldn't that be like if you like just fell from the sky?
It would mean if you instantly fell out of the sky.
Yeah.
Like you were like in the air, on the ground. Boom. So it's not even we crashed. We like teleported to the ground.
Yeah.
Which obviously that's wrong too. So I'm sorry, my computer's gonna try to save this program, and I'm gonna say don't save. So that wasn't it. That's not what I wanted. I wanted probably something that looks like this. And I'll be honest with you, I think that this is quite a very big slope downwards. I mean, this is where like the pilot's like, I'm done flying.
They have to go to the bathroom or something. So
boom, and then he just kind of like, that's almost an instantaneous slope. Yeah. So I mean, maybe draw it out a little bit longer or whatever, or your graph is going to look a little bit different from mine because mine is like Mr. Crazy Pilot went on like, I need to go and see my I need to go to the bathroom really bad. You know, let's land this plane now.
Have to.
Got it? Yeah. The pilot says, "Hey, you guys want to have some fun?" All right, listen to this one. Malia? That's not how you spell Malia. Oh, these guys trying to be Hawaiian. They can't even spell Malia. Malia uses her cell phone constantly during the day and often runs her battery out. On one particular day, she leaves home with only a half charge. She talks on the phone with her friend the whole way to school. When she gets to class, her battery is nearly drained. So she asks the teacher if she can change her or charge her phone. The teacher says allows her to do it just this one time, which Mr. Dalday will not allow you to do. Actually, I'm fine with it. I don't care. During class, she gets 2/3 charged and heads to her next class. The next teacher likes to incorporate technology into his lesson and asks the teacher to respond to a poll with Malia's cell phone battery is completely drained. Oh my goodness, there's just so much to this story. Whatever. All right, let's do it. And I'll tell you what, I'm not going to ask you. I'm just going to start going through this quicker because we've been sitting here doing this for a while. All right, you start off halfway. Talk on the way to school. Talk with your friend. Goes down to almost 0. Got it? Your teacher allows you to charge the phone in class. Let's say class is maybe like an hour long. And how long does it take for you to charge your phone? I got a question. Does it take longer to charge your phone than it does to drain your phone?
Yeah.
I have a pretty junk phone, so I mean, mine has to charge all night.
Yeah, mine.
What I mean is like, Does it take you longer talking on your phone to drain it from full battery down to 0 than it does to take a phone that's at 0 and charge it to the full battery?
Nah. I think I can charge it. No, I think I drain it faster than I can charge it.
You drain yours faster? What do? Talk and use Facebook and
I just don't close
chat
the
at the same
apps.
time?
I don't close anything.
Yeah, you're the person who takes selfies while talking and do FaceTime and take pictures while using your app.
I just leave it on and forget about it.
All right, whatever. Okay. All right. Usually it charges faster than this stuff. All right. All right, fine. Your phone is slow. Let's make it charge real slow then. Got it.
Well, I mean, whoever. I don't care. I mean, I don't know.
I'm just messing with you.
I know.
All right. All right. So it goes up to 2/3 of the way, and then what does she do? She goes and talks, or the other teacher drains the cell phone because of some app that he's using, and then the next 2 teachers won't let them charge the phone. So 0 and 0 for the next 2 teachers, and then when she gets home, she plugs it in and gets a full charge. Sound good?
Yeah.
That would be the graph. We cool?
Yeah.
All right. By the way, I have no ideas about cell phones. I'm assuming that they're talking about a smartphone, and I don't. I have a very dumb phone. Last one. Sophia wanted me to talk about 2.2. Ooh, these look fun. All right, let's talk about these ones. And I don't think I gave you home. I don't know if I gave you homework on these. I don't think I did, but let's try them because they're not easy. I have this thing right here, and it looks like a ipu. Like like the. Ooh.
That's a good drawing.
Right. All right. So I've got the ipu, and oh, this is homework 2.2. Ooh, so you got Mr. Dahl. You tricked Mr. Dahl into doing homework for you. All right.
Clever.
All right. Clever. All right. I'll tell you what. I'll do 2 of them for you, and you do the other 2.
Figure the rest out.
Sound fair? I'll do the bucket and the ipu, and I'll start with the bucket because the bucket's easier. Now I think that the way the homework is each container below is placed in the faucet once at a time and turn on. The faucet is turned on and left at a constant rate. For each of the following page, or for each on the following page, draw a rough graph of the height of the water containing of the water in the container versus time. So we're talking about the height. Okay.
Let me draw this.
If this bucket were a straight up cylinder, it was just a straight cylinder, had straight sides, how would that graph look?
I imagine that would be filling up at a constant rate, and
Be
so it would
constant.
be like a straight line.
Exactly, very good. But this, it would be a linear slope. It would be a straight linear slope means line slope, or linear positive slope. I agree. Very descriptive words. It'd be a line that has a positive slope. Good.
Yeah.
But this bucket has tapered edges, so it fills up. I would say it fills up faster when it's down here versus when it's up here.
Yeah, since there's more to fill. Wait, really quick. What would each represent?
Okay, this would be probably time, and this would be h.
Height of the water.
All right. Yes, I would agree with Sophia. I would say it still goes up, right? So like this would be, if it were a cylinder, it would look like this. If it were just a straight cylinder that's like this big, right?
Yeah.
But since it's not a cylinder that's that big, it kind of tapers down like this.
Yeah, because it'll take more time to fill up all this space with water.
Yeah. So the height would take more time. Do you guys agree?
Yeah.
In fact, Sophia, what does that graph look like? And I'm asking Sophia specifically for a very specific reason. It's a square root function. The one we talked about, that confusing function at the very beginning. Yes, exactly. It's a square root function. And do I actually know the formula? Actually, I bet you that the function is going to have a square root in it. I think that's really interesting, how it all comes back to that. Anyway, let's talk about this one. How's this graph going to look?
This graph.
All right, I'll tell you what. Why don't we do one circle?
One
Let's just
circle.
cut this thing off and just do one circle. All right, this one is probably going to look like this. From filling up between here and here, if this were time and this were h, I would say that it goes up slowly. So it's going to kind of go like this and taper down like this. Does that make sense?
Yeah.
And then it's going to fill up fast as it comes over here.
Yeah.
So something like that.
I'm trying to understand how the graph works. Okay, so the time.
And then for the second circle, it will probably do something just like that as well.
That's not as confusing as I thought it was going to be.
And I feel like this is actually makes sense to me because you guys ever fill up water bottles?
Yes.
Or milk jugs. You ever fill up milk jugs?
Probably once.
And the milk jugs kind of taper off at the very end. And you ever notice that when you're filling up the water bottle, you fill up the water, it goes, and at the very end it just goes,
Yeah.
and it almost like spits out.
Yeah, it's like slow and you're waiting. And
It's because the thing goes from a constant cylinder to like this tapered thing at the top, and so it spits up real fast because it doesn't require as much volume to increase its height.
Yeah.
That's where I'm getting this part right here.
Okay.
That's kind of the idea behind it. Does that kind of make sense to you?
It's like small right there.
Yeah, because I'm talking about this area right here.
Okay.
It's tapering in, so it fills up much quicker.
Yeah, that makes sense.
I hate to say this, but there is no real math here. It's really just kind of maybe logic or just past experience or work your way through this.
No, yeah, I couldn't see how it's a logic thing based on just the way it looks.
Yeah, it's visualizing, but this is very important stuff to do with math. Okay? So anyway, here's what my graph would look like. It would look like kind of a snake looking thing. But here's my question: is would it look like this?
No.
No.
Because I feel like that would be the time thing.
See that right there? That's not a function.
Oh yeah, it goes through multiple times.
Yeah, your vertical line goes through multiple times. So the graph, I would say, looks more like this.
Let me write that down too, or else I forget.
Got it?
What is that called? The vertical line test?
The vertical line test, yes. All right, folks. I've talked until I'm tired. Man, I talked and I only get a 15-minute break before chemistry. So get out of here. You have chemistry in 15 minutes.
Good luck to those people.
Yeah, I know. Good luck to those people because, man, chemistry is going to be a lot of math as well.
Yeah.
Today is going to be... Your Mr. Dalday can be a machine. I'm just